All right, we're on page 259. We need to talk about sigma notation. All right, Greek letter sigma. It's the S, sum, sigma, sum. Okay? Now, here's what the definition of sigma notation is up here at the top of the screen. It means this. If we have several terms, all right, now you need to look at this. We start with the sigma itself. Wow, that's a bad one. Dun, 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 dun. That's a good one. Okay? Now, we have what's called an index of summation. Usually I, sometimes J, sometimes K, can be anything. I for index makes the most sense to me. Okay? We have an upper bound of summation and a lower bound of summation. Those are both constants. And in fact, they're whole numbers. Okay? We usually start at 1 because, I mean, when you start counting, you like to start at 1. You don't have to. You can start at 0. You can start at 3. So you will see an actual number written right here. Okay? That tells you where to start counting. You count up until you reach N. So sometimes you'll see an N. Sometimes you'll see an actual number, like instead of an N, a 7. So we will count from 1 to 7. 1, 2, 3, 4, 5, 6, 7. Okay? So in this example here, the way I'm writing this, 1 is your lower bound of summation. N is your upper bound of summation. All right? Then we have terms. These terms are called A. Okay? Now, we put a subscript of I, or whatever your index of summation is. For us, it's I. Now, what happens then is as we count from 1 to N, 1, 2, 3, 4, until we get to N, that subscript changes every time. So if we start counting at 1, A1 is the first term of the terms we're adding. A2 is the second term of the terms we are adding. And you keep going until you get to the last term, which would be A with the subscript of N. Okay? So that's what that notation means. It's all right there, but sometimes it helps to see the order you come up with it. Everybody with me? All right. Now look at example 1 from your book, because I couldn't do it any better. So I'm doing example 1 from the book. All right, in A, we have the sum from I equals 1 to 6 of I. So I is the index of summation. 1 is the lower bound of summation. 1's where we start counting. 6 is the upper bound of summation. 6 is where we stop counting. And all of our terms look like I. So if we start with 1, the first term then has to be 1. All right? Then we count up to 2. Second term is 2. We count to 3, 4, 5. We stop at 6. That's what that notation means. Okay? Now look at B. This time, what's our index of summation? All right. I. What's our lower bound? 0. What's our upper bound? 5. And our terms aren't just I anymore. Each of our terms looks like I plus 1. So we start counting. We start counting at 1, 0. So if I replace that I with a 0, our first term is 0 plus 1, 1. Then I count up to the next number. Our next number is a 1. So I replace that I with a 1. So our next term is 1 plus 1, 2. Then I count up again. Now I'm up to 2. So I replace I with 2. So our next term is 2 plus 1. 3. Then I count up again. Now I'm up to 3. So our next term is 3 plus 1, 4. Get it? And so then our next term is 4 plus 1, which is 5. Our last term is 5 plus 1, which is 6. Notice anything about the two things I circled? The same. So different sigma notations can represent the same sum. We'll see why we might want that later on. Okay? And then look, we can make this as complicated as we want to make it. We make it complicated by making each term more complicated. Okay? So here in part C, our index of summation is J, our lower bound is 3, our upper bound is, so we're just counting from 3 to 7, 3, 4, 5, 6, 7. Okay? And then look what our terms look like. They're all J squared. So when we start counting at 3, our first term is 3 squared. Then we go up to 4. So our next one is 4 squared. 5 squared, 6 squared, stop at 7 squared. Okay? Notice on any of these, have we actually worked out the answer yet? No. Can we? Yeah, you just got to add. Okay? Now look at D. This time our index of summation is K. Our lower bound is 1. Our upper bound is N. And look what our terms look like. Now, N is a constant. N doesn't change as you count. K changes because it's the index of summation. So, since our lower bound, oops, I meant to erase. Since our lower bound is 1, for the first term then, we replace K with 1. So look what the first term looks like. It's 1 over N times 1 squared plus 1. Then we count up to 2. We replace K with 2. So look what our second term looks like. 1 over N times 2 squared plus 1. Then the next one would be 1 over N times 3 squared plus 1. And then 1 over N times 4 squared plus 1. Until we finally get to that last term. Still with me? Okay. Now, E is what we're aiming for. Okay, you're going to see E again. What's the lower bound, or excuse me, what's the index of summation? I, that's the way I like it, I. The upper bound is 1. No, the lower bound is 1. The upper bound is N. And each of our terms look like this. So, what changes as we count up? Just the I. The index of summation is what changes. So look, for our first term, everything stays the same except the I becomes a 1. For our second term, everything stays the same except the I becomes a 2. Then the next term, the I is a 3, then a 4, then a 5, then a 6. And the last term, the I becomes the upper bound of summation. In this case, it becomes an N. You with me? Now, here's why we're going to see this one again. Because the goal of today's section is to learn how to find, or actually approximate, an area underneath a curve. You've found areas of geometric figures. You did that with me 3 years ago. All right? Now we're going to find areas of things that look like this. We're going to find that area. And the way we're going to start off doing it is by approximating it by putting little rectangles under that area, or into that region, I guess I should say. And how do you find the area of a rectangle? Length times width, or base times height, right? Well, look, if I've got a rectangle sitting on the x-axis here, isn't the height of that rectangle whatever that y-coordinate is? And can't y coordinates be called f of x? And isn't the width of that rectangle whatever the difference between that x coordinate and that x coordinate is? And don't we call the difference in x coordinates delta x? So that represents the area of the first rectangle. That's the area of the next one. Then we get the area of the next one, the next one, the next one, the next one, till we finally get the area of the last one. We add them all up, and we have the area of all those rectangles, or the sum of the areas of those rectangles, which will be an approximation of the area under that curve. Okay? Question? We did this the very first day. We sure did. We did this the first day. Okay. All right. We need some formulas because if your index, if your upper bound is big enough, then it's just not practical to work it out by hand. Like if we're trying to find the sum from 1 to 10 million of a fairly complicated term, we're not going to ever be able to do it. Okay? So fortunately for us, over the years, mathematicians have worked out these properties, their theorems of how these summations work. Now, look at the first one here. This is on page 260 in your book at the top. Look at the very first property right here. All that's doing, k is a constant, all that's doing is saying you can factor out a greatest common factor. For instance, if I had 2 plus 4 plus 6, couldn't I factor out a 2 and make that 2 times the quantity 1 plus 2 plus 3? Right? Aren't those equivalent? That's what that first property is saying you can do. Because if we wrote that out like we did these, it would be a series of terms added together, wouldn't it? Each one of those terms has a factor of k. You can factor out that greatest common factor of k and then work out the sum and then multiply it by k. We could work out the sum and multiply it by 2. See what's going on? So, since you can factor out a constant from a series of terms that are added together, you can factor out a constant from a sigma and put it in front of the sigma. All right? Now, when you add, or in fact subtract, does it really matter what order you go in? For instance, if I had like 2 plus 3 plus 2 plus 4 plus 2 plus 5, couldn't I add together all the 2's first and then add together the 3, the 4, and the 5, and then add that together? I could, right? That's what this property is saying. If you've got the sum of 2 or more terms added or subtracted together, you can make it the sum of the first one plus the sum of the second one plus the sum of the third one plus the sum of the fourth one, however many of them you have. We can do that because what are sigmas? They're sums. And with sums, you can regroup any way you want to, can't you? So we can with sigmas. All right, so those properties make sense? Haven't we done that with limits? That's essentially what we did with limits, right? We said if you have a factor or a common factor, you can put it in front of the limit sign. And if you've got the limit of 2 or 3 terms added together, you can take the limit of the first term plus the limit of the second plus the limit of the third. Works the same way. Okay? All right, now let's look at these summation formulas. If you have the sum from I equals 1 to n of a constant, the sum is simply that constant times n. Think about it. If you've got the sum from I equals 1 to 3 of 7, wouldn't that just be when I equals 1, there's no I to change, it's 7. When I equals 2, the term is 7. When I equals 3, the term is 7. So wouldn't it be easier to just multiply your constant times your n to get the answer? Okay? Now, I'm not going to work an example of each of these theorems because that would take forever. But you have the sum from I equals 1 to n of I. So in other words, you're just simply counting. Add 1 plus 2 plus 3 plus 4 plus 5 plus 6 until you finally get to whatever that upper bound is. Turns out it's this. It's the upper bound times the upper bound plus 1 divided by 2. And our book even tells us how this came about. When a guy named Gauss was a student, and this is pre-calculator days, obviously, since there's his dates. Teacher told him to add up all the integers from 1 to 100. He did it like that. Here's what he did. He wrote them all out from 1 to 100. Then he wrote them all out backwards. Then he added down each column, and you get 101 every time, don't you? So he has 101. So the sum down here is 100 times 101. But isn't that 2 times bigger than he wanted? Didn't he add each number twice instead of once? Divided by 2. Yeah. He was what's known as a genius. Okay? So that's where that... So I always heard that he was 6 when he figured that out. I don't know if that's true or not. I hope it's not, because that's just sort of embarrassing. When I was 6, I couldn't have added 2 plus 3, I don't think. All right, number 3. We have the sum from I equals 1 to n of I squared. And that's this nice, attractive little thing here. And then the fourth one is the sum from I equals 1 to n of I cubed. And it's that one. You'll need to know these. You'll memorize them as you use them, so don't make a big deal out of it. Okay? Y'all still hanging in there with me? Yeah. All right. Now, to evaluate a sum, we want to apply those properties and theorems. If your upper bound, of your summation is small enough, you can just crunch it out, can't you? Just, figure out what the first term is, plus the second. But if that is your upper bound, I don't care how simple your term is, you don't really want to spend the next few hours adding 1 plus 2 plus 3 all the way up to 10,000, do you? So use your properties to make this easier to work with. So look at this example 2 here. All right? We start with the sum from I equals 1 to n of I plus 1 over n squared. Now, n is a constant, which means n squared is a constant, which means 1 over n squared is a constant. We have a property that says we can take constants, set them in front of the sigma. So we've made it simpler already, haven't we? Then we have the property that says if you have the sum of 2 or more terms, make it the sum of the first one plus the sum of the second one, and so forth. So that's what they did there. There's a formula that turns that into that, and a formula that turns that into that. So that gets us this far. Then you do a little arithmetic inside the bracket. Then you multiply by 1 over n squared. Can you work with that formula? Can you stick a 10,000 in there and get an answer now? Now you can. Whereas if you just used the summation notation without using any of its properties or any of its theorems, this would be a problem that you could never finish. But by working with the properties and the theorems, you've turned it into a problem that on your calculator you can do in about 10 seconds? Okay? All right. Now, notice that n is a constant as far as the sigma is concerned. I is the variable. The index of summation is the variable. Anything else is a constant. Okay? Only the I changes. Now, where we're heading with all this. Like I already told you, we're going to find areas. So if you'll look on page 262 with me. The area of a plane region can be approximated by finding the sum of the areas of rectangles. So just look at the two pictures I have up here on the screen. Here in figure 1, all they've done is they've put rectangles underneath the curve, where the height of the rectangle is always less than or equal to the curve. Okay? That's called a lower sum. And the rectangles that fit underneath the curve are called inscribed rectangles. So the lower sum is found by using inscribed rectangles to approximate the region. So if I find the area of 1, 2, 3, 4, 5, those 5 rectangles, if I find the area of each one and then find the sum of those areas, that sum will be less than the actual area of this region we're trying to approximate, won't it? If I go the other way and I make it so that the height of the rectangle is greater than or equal to the actual f of x on the curve, that's called the upper sum, and those are called circumscribed rectangles. If I find the area of each of those 1, 2, 3, 4, 5 rectangles, and then the sum of those areas, that sum will be greater than or equal to the actual area of the region, correct? So we'll have narrowed it down. The lower sum, the actual area of the region is somewhere between the lower sum and the upper sum, correct? That's what we do. Okay? Now, just so that you're not left wondering, like we talked about, and it really was the very first day of class, how do we get a better approximation? More, meaning smaller, rectangles, right? The more rectangles you put in, the skinnier, the narrower each one is. Or the narrower you make each one, the more of them you have to put in. So whichever way you think about it, by putting in more rectangles, you will get a better approximation. Yes? Yeah, I don't think you're going the right direction with that. All right. So here they have more rectangles. On the left, that would be a lower sum. On the right, that would be an upper sum. And the area of the region somewhere in between. Okay? Now, it's going a little bit out of fashion to do lower sums and upper sums. It's becoming more into fashion to talk about left-hand Riemann, I haven't used the term Riemann sums. Let's go left-hand sums and right-hand sums. Okay? Like this. So this figure is also a representation of a right hand. We'll define Riemann sum in the next section, but what we're working with are Riemann sums, okay? Riemann's a person's name, mathematician's name. Since it's called a right-hand sum, since the right end point of each interval is used as the height of the rectangle. So, that's the right-hand part of that first interval, isn't it? That's how you get the height of the rectangle. That's the right edge of the next interval, and that's how you get the height of the rectangle. Do not confuse, do not assume that right-hand sums are always lower sums, because if the concavity went the other way, wouldn't it work differently? Okay? So don't assume that right hand means lower or lower means right hand. They're two different things. One's kind of coming into fashion, one's kind of going out of fashion. Okay? I don't know why. All right? So, if the top corner of the rectangle is that hits the graph is the right top corner, it's a right-hand sum. If the top corner that touches the graph is the left end, then it's a left-hand sum. Okay? So you're with me on right hand and left hand? Okay. Now, as the number of rectangles approaches infinity, we put more and more rectangles in there. The lower sum and the upper sum have to get closer together, don't they? They have to get closer to each other because they're becoming better approximations. So therefore, they are becoming closer to the actual area of the region. Now, the area of a region, and I would write this down if I were you, equals the limit as the number of rectangles approaches infinity of the sum of the areas of the rectangles. The area of a region equals the limit as the number of rectangles approaches infinity of the sum of the areas of the rectangles. And while you're writing, I'll remind you that the number of rectangles approaching infinity is the same idea as the rectangles getting more and more narrow, isn't it? Okay? The number of them approaching infinity and the width of each one approaching 0, never equaling 0, then they don't have a rectangle, is the same idea. Do you see that that's the same idea? All right. Now, I think this will make more sense if I work this backwards. So let's start and say we have the area of a rectangle. And then we're going to, so one rectangle. And then we put in another rectangle, another. We put in, I don't know, 6 of them, 8 of them, 10 of them, whatever. If we find the sum from I equals 1, 2, however many rectangles we put in, we'll call it n, that's our approximation, correct? I don't care, our approximation of the area of the region. I don't care if the rectangles are inscribed, which gives me a lower sum, it's still an approximation. I don't care if the rectangles are circumscribed, which gives me an upper sum, it's still an approximation. I don't care if some of them are inscribed and some of them are circumscribed. I still get an approximation, don't I? Now, the more of those rectangles I put in, the less it matters if they're inscribed or circumscribed. Because they're so narrow and there's so many of them, I will get a better approximation. Let's face it, putting in, if I have a region that looks like this, there's the x-axis, putting in one rectangle doesn't give me a great approximation. Putting in 2 is better, isn't it? And then 3 is better than 2. And 4 is better than 3. And 10 million's better than any of that. And 10 trillion's even better. And then 10 trillion raised to the 10 trillionth power is even better. So we're making these things so narrow that they're going to fit the region. We're finding the limit as the number of rectangles approaches infinity. And that equals the area of that region. Equals. Not approximate anymore, because we found the limit as n approaches infinity. We found the sum of an infinite number of rectangles. So, that's the way that should look in your notes. Did you follow me working it out backwards? And it does kind of make your head want to explode, doesn't it? Now, we talked about this a few minutes ago. How do you find the area of a rectangle? Length times width, or base times height. I don't care. It's the same thing. Okay? Which means we can write the area as, all right, the limit as n approaches infinity. That's good stuff. We leave that. The sum from I equals 1 to n, beautiful. Leave it. But area of a rectangle, that's not written in such a way that we can compute it, is it? But the area of a rectangle is base times height, or length times width. the height of the rectangle. Let me draw another sketch real quick. That's our region, and I'm just going to draw in one rectangle. The height of the rectangle is that y-coordinate, isn't it? Y-coordinates can be called f of x. I'm going to write it as an x in just a minute. I'll call this one f of c because the height depends upon that particular x coordinate, but I'm going to generalize it and call it x in just a minute. So that's the height. And then the base, like we talked about a while ago, it's the difference. If I call that x2 and x1, it's just x2 minus x1. It's delta x, isn't it? We've called it delta x, we've called it dx. It's always meant the difference between two x coordinates. The difference between those two x coordinates is the width of the base of that rectangle, correct? So we'll call it dx, and that represents the base. So I'm writing it as height times base, but same thing as base times height. Okay? So the f represents the height, the delta x represents the width of the rectangle. Now, in general, and this is where your notes need to end, we don't want to look at that right yet. Right here's where your notes need to end. In general, area equals the limit as n approaches infinity of the sum of I equals 1 to n, and I'm going to call it f of x sub I, because I'm going to find the sum. I realize I'm going to be moving from one x coordinate to the next. So by I changing, the x coordinate changes every time we find a new rectangle, right? So first it's x1, whatever that is, then it's x2, then it's x3. So we can call it x sub I delta x. And then like we did back with differentials, delta x equals dx, doesn't it? Okay? So area equals the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I dx. Everybody got it? Huh. We ever seen anything that looks like that before? You're getting really close to knowing why the mysterious dx is there when we do indefinite integrals. Really close to knowing. Let's do a few. Oh, I didn't mean you were going to find out today. I bet you could figure it out, though. Page 267. Number 6. Says find the sum and then use the summation capabilities of a graphing utility to verify your result. I'm not sure I would do that. Find the sum. So we've got the sum from I equals 1 to 4 of, and then this horrible looking thing, I minus 1 quantity squared plus I plus 1 quantity cubed. Now, I could square that first parentheses, cube that second one, combine like terms, and then try to apply properties and theorems of our sums to this. Or I can crunch it out. I can just do the computation. Since it's just going to be 4 of them, because I goes from 1 to 4, I think we're better off just sucking it up, putting a 1 in there for I, figuring out what we get, then put a 2 in for I, figure out what we get, then a 3, then a 4. So that's what we're going to do. So first, I put a 1 in there. Then I put a 2, then a 3, then a 4. Now, I'm going to hustle on through this. You can work this out on your own. But yeah, all I did was I just simplified each of those terms, right? For I equals 1, I simplified that and got 8. For I equals 2, I simplified it and got 28. When I equals 3, I got 68. And when I equals 4, I got 134. Then I added those together. Okay? So if you want, write down that the answer is 238 and then come back and fill in the work. But we got tougher fish to fry than this one, so we need to move on. All right? Let's take a look at number 12. I find these problems to be about the most difficult we can have with sigmas. When they give us something written out in expanded notation and expect us to be able to put it into sigma notation. All right. So what we need to do is examine our terms here. All right. So our first term is that. Our last term is that. Well, the things that stay the same stay the same. Okay? So what do our terms look like? Well, they've got a 1 in them. Then they've got a negative sign. Then they've got a big old parentheses with stuff in there. Now that and that are a little different. If it change, in the summation notation, in sigma notation, the only thing that changes is the I, isn't it? So there must be an I going on there. Look, the 2 stayed the same, the N stayed the same, but that N showed up. Now, if our sum starts at 1, which a lot of them do, right? If our sum starts at 1, would you have even seen a 2 times 1 right there? You wouldn't. So if that's a 2 times 1, doesn't it make sense that at the end it would be a 2 times n if we made our summation go from 1 to n? Yeah. So I think that's what's happening. So from 1 to n, that must be an I. And then what else do we have? Well, in the yellow, we have a minus 1. In the green, we have a minus 1. That didn't change, so it doesn't change. Outside that parentheses, we have an exponent of 2. In both of them, we had a bracket. In both of them, we have a 2 over n. So that's got to be it. The only thing that changed was here. That must be where the I is. Make sense? All right. So you're good with what I have written. If you want to, since 2 is a constant and n is a constant, if you want to factor those out and put them in front, that's okay too. If this were a quiz question, I'd be pretty excited that you got that. Wouldn't you? All right. And I think those are the toughest ones. I have a hard time working backwards with those. And since I do, then you probably will, because I'll screw you up when I explain it to you. Number 18. Use the properties of summation and theorem 4.2. So use the properties and the theorems to evaluate the sum. All right, so we've got the sum from I equals 1 to 10 of I squared minus 1. One of our properties says that if we're finding if our term is actually 2 or more terms, we can make that the sum of the first one plus the sum of the second one. In this case, it's actually minus the sum of the second one, isn't it? So the sum from I equals 1 to 10 of I squared minus the sum from I equals 1 to 10 of 1. Do we have a theorem that tells us how to find the sum from I equals 1 to 10 of I squared? Yeah, we do. Turns out that's n, which is 10, times n plus 1, which is 10 plus 1, times 2n plus 1, so 2 times 10 plus 1 over 6. That was n times n plus 1 times 2n plus 1 over 6. And then we also have a formula that tells us the sum from I equals 1 to n of a constant, don't we? It's the constant times n. So it's the constant times n. I'm seeing blank stares. Is it blank stares because why does he keep explaining that? I get it. Or is it blank stares because is he still talking about the same subject we started the class with? Or is he now talking about nuclear fission or something? Yes. I have these. I have. Where is it? All right. I've got that one, and I've got that one and that one. All right. What 140? 1 times 10. Now, that's C times N. 1 times 10. All right, we got to keep going. Number 29. Use upper sums and lower sums to approximate the area of the region using the given number of subintervals of equal width. I'm going to have to get you started on these and then leave you hanging. So, they've given us 1, 2, 3, 4, 5 rectangles. All right? So what we want to do is find the area of each rectangle and then add those up. So our first rectangle, this is a lower sum, so that is our first rectangle. Now, these intervals, these 5 intervals they made were all the same size. So look, the distance from 1 to 2 is 1, so wouldn't the width of each rectangle be 1/5 or 0.2 if you prefer? Okay, so the area of that first rectangle is base 0.2 times, well, then you got to figure out the height. So look where that y coordinate is. This is a right-hand sum, isn't it? So follow that down. What's that x coordinate right there? It's not 1, it's 1.2. Our function is that, so f of x, the y coordinate then, is 1 over 1.2. See how that gives you the area of that first rectangle? A base of 0.2, a height of 1 over 1.2. Now, plus, we need to get the area of the second rectangle. So, here's your second rectangle. What's its width? Its base? 0.2 times, now to get its height is 1 over x. It's f of x, which is 1 over x. It's that y coordinate right there is the height, isn't it? Again, because this is a right-hand sum. Follow it down. That x coordinate's not 1, it's not 1.2, it's 1.4. If we're going in intervals of 0.2, it's 1.4. So that's the area of the second rectangle. See what's going on? So the area of the third one is going to have a width of 0.2 again, and the height's going to be 1 over 1.6. The next one, a width of 0.2 again, the height will be 1 over 1.8. The last one, width of 0.2, and the height will be 1 over 2. All right, now, save the number crunching. Do you understand that? Maybe I should ask it this way. Do you have any questions that you're able to articulate about that? You may have to go home and mull it over for a while before you can even ask a question about it. It's the height is the y coordinate. So I just found the top edge of each rectangle. For the first rectangle, that's the top corner. It touches the graph, so that's how I find the height. For the next rectangle, that's the corner that touches the graph, so that's how I find the height. Now, go back and look at this video when you get home. Hit pause right now. 1, 2, 3, pause. Oh, now I can't tell you to unpause because you've paused it. At some point, maybe you'll figure out to unpause to see the rest of it, and that way you'll be able to figure out how to work out that upper sum. Think about it. It'll make sense. Maybe. Next week it'll make sense. Maybe it will this weekend. We'll see. We're not done. We're not done. $31. That's what it's asking you to do. I just wasn't sure you would understand the directions. They want you to find the limit as n approaches infinity of 81 over n to the fourth over n squared times the quantity n plus 1 quantity squared over 4. And I'll even put that on the video so you can check your work. But the big thing was I didn't know if you would understand the directions. Okay? And I really hate to do this. Again, you can hit pause. Don't forget to unpause. Yeah, I got to do it, and you got to do it. The semester's running out. No putting it off.